Hi everyone. So we're looking at section 3.2, 3.3 today. So this is actually continuing our discussion about how to solve polynomial equations, basically, right? And so in this case, we're actually going to be looking at some different rules and theorems, again, to see how we can better solve our polynomial equations and maybe get the answer for them. So remember, we were talking about finding zeros for them last time. So let's start with this first one here. So we're saying the number of roots of a polynomial equation. So this one here is basically talking about how many roots or how many answers should a polynomial equation have. So as you can see here, we're talking about when a polynomial equation is solved by factoring. A factor may occur more than once. So looking at this example here, you've got x squared minus 10x plus 25 equal to 0. So if you factor this quadratic equation here, it actually factors into x minus 5 and x minus 5. So this x minus 5 squared, basically means you have x minus 5 and x minus 5, right? That's why we're writing it to the second power. So basically what we are saying here is that you have the same factor, x minus 5, that occurs twice. So basically we can say 5 is the root of the equation, but since it occurs twice, right, from this factor of x minus 5, we will actually say it has a multiplicity of 2, which basically means that it's coming from two of the factors which happen to be the same factor, and in this case that's x minus 5. Okay, so your definition for multiplicity is basically saying if factor x minus c occurs k times, so k is how many times it occurs, right? Is it 2 times, 3 times, more than that? In the complete factorization of the polynomial function, which is our p of x, then we would say c is a root of that polynomial which has a multiplicity of k times. So basically we're saying if you take this x minus c factor, set it equal to 0, you're going to get the answer as being c. And if this factor x minus c occurs k times, the multiplicity of our root is also going to be that same k value. So they are saying if a root with multiplicity 2 is counted as 2 roots, then we can say every quadratic equation has 2 roots, which would be the set of complex numbers. Because remember, basically, whenever we're talking about complex numbers, we're talking about real answers or imaginary ones also, right? Okay, so this end-root theorem is actually kind of tying it with this multiplicity definition. So we're saying if we have a polynomial function p of x set equal to 0, and it can have real or complex coefficients, which means real or imaginary coefficients. But if your polynomial equation has a positive degree of n, then we would say when multiplicity is considered, you would basically saying, including this idea of multiplicity, you would have n number of roots. So if it's a second degree polynomial, we should have 2 roots. If it's, let's say, a 4th degree polynomial, then you should have 4 roots. Remember, we had kind of talked about this before also. Okay, so let's look at our first example here. They're asking us to find what the roots are, and of course we need to talk about multiplicity. So if the same root is occurring more than once, then we will talk about multiplicity in that case. Okay, so let's go ahead and take a look at our first example here. Okay, so for this first example, as you can see, this is actually already given to us in the factored form, and they're asking us to find all the roots, including the multiplicity. So basically what we're going to do is we're going to take each factor and set it equal to 0. So we've got x cubed equals 0, or the quantity x plus 2 to the second power equals 0, or that last factor 2x minus 5, and set that equal to 0. Okay, and then we're going to solve each one of these individually, and that should be a 5. Let me write that one more time. Okay, so I'm going to start with the first one. So you can see this is x to the third power. So to get x by itself, of course, that means we're going to have to take the cube root on each side, right? To get rid of the third power, you use the third root. So cube root will cancel out this cube, and you will, of course, end up getting x. Now remember, with cube roots or any odd root, you don't have to worry about positive or negative sign. So you get x on the left-hand side, and then cube root of 0 would, of course, end up being 0. Now here's something we got to think about. This x equals 0 was coming from the factor which is x raised to the third power. So since this guy was raised to the third power, we would say x equals 0 has a multiplicity 3, right? Because again, like I said, since this is a x to the third power, that third power tells us our multiplicity is going to be 3. Okay, so that's for the first one. Now for the second one, we have x plus 2, the whole quantity raised to the second power, right? So to get rid of that second power, we would of course need to use square root. So to get rid of the second power, we're going to use square root, and of course you're going to do square root on the other side. But then with square root, we need to remember that we get one positive and one negative root. So again, square root will cancel out the square. We will be left behind with just x plus 2. And then square root of 0 is 0. And then we know 0 does not take a plus or a minus sign. So you don't have to put plus or minus on 0. So all we have to do now is get x by itself, move the 2 to the other side. So these guys will cancel out, giving you x equals negative 2. And since x equals negative 2 is coming from this factor of x plus 2 to the second power, we will say this guy has a multiplicity 2, right? Because since this is the second power, you would have a multiplicity of 2, which will bring us to that last factor, 2x minus 5. So again, we're trying to get x by itself. So start by moving that 5 to the other side. So these guys cancel out, leaving us behind with 2x equals positive 5. Go ahead and divide both sides by 2. And then you end up getting x equals 5 over 2, right? And this is, of course, coming from the factor of 2x minus 1. Now you will see 2x minus 5, not 2x minus 1. 2x minus 5, and of course you can see 2x minus 5 was not raised to any exponent, which actually tells you this only occurs one time. But if you want, you can say it has a multiplicity of 1 because this guy had no exponent on it, so it's understood that your exponent is 1. So this was, of course, given to us in the factored form. But if you look at all the x powers, you have x to the third power here. Since this is raised to the second power, your x would be to the second power for x plus 2. And then this x here is, of course, just to the first power. So this is actually a 6th degree polynomial, because if you add up all these numbers, 3 plus 2 plus 1, it adds up to 6. So you will actually have 6 roots for this polynomial. So we've got 3 roots from here. We've got 2 roots from here, so that's 5. And we have 1 root from here, so that's 6. So for a 6th degree polynomial, you will have 6 roots when you solve this. So this is kind of what that n root theorem is talking about right here. So that's what this theorem is talking about. Okay. The next theorem that we want to look at is what we call as the conjugate pairs theorem. So when we're talking about conjugate pairs, we're talking about binomial terms basically, where your terms will be the same, but the sign in the middle is going to be different. So something like this. If you have one factor, I guess you can call it, as a plus b, then its conjugate pair is going to be a minus b. Okay, so the idea is your terms would be the same. So it's the same a and b, but the only difference is you have plus in one of the pairs and you have minus in the other. So this was, let's say, if we were talking in terms of real numbers. Now, if we were talking in terms of complex numbers, which is real and imaginary, your conjugate pairs would end up looking like a plus bi, right? So a would be the real part and bi would be the imaginary part. So its conjugate pair would then end up becoming a minus bi. Okay, so that's what we mean by conjugate pairs. Now let's take a look at what the conjugate pair theorem says. So again, if you have a polynomial function p of x equal to 0, they're saying this is a polynomial equation that has real coefficients and it can have these complex numbers as their roots. Then basically what they are saying is if your polynomial equation has a plus bi as one of its roots, then that means its conjugate pair a minus bi is also going to be a root. So they're basically saying if you solve a polynomial function and you get a plus bi as one of its roots, that means automatically a minus bi is also going to be a root for that same polynomial function. So just as an example here, we've got x squared minus 2x plus 5 equal to 0. So you can see we use the quadratic formula here to help us solve this equation. So when we solve this equation, you can see both 1 plus 2i is our root and 1 minus 2i is also our root. So these would what we would call as conjugate pairs. So if one conjugate term is going to be a root, then the other one is automatically going to be a root. So that's what this little statement is saying here. So the roots 1 minus 2i and 1 plus 2i are your complex conjugates, and they're saying the plus and minus symbol in the quadratic formula will basically cause your complex solutions to have real coefficients that would end up as conjugate pairs. Okay, so let's see how we can use this idea of the conjugate pairs theorem here in this next example. So they're actually asking you to find the polynomial function. So we're working backwards. They're saying the polynomial equation has real coefficients and it has roots 3 and negative I. Okay, so you can see 3 is going to be a real number, but negative I is an imaginary number, right? So the idea is if you use this concept of the conjugate pairs theorem, then that means if negative I is your root, then that also means that positive I is also going to be a root. Let me write that a little bit better. So, like I was saying, if negative I is a root, then positive I is also a root. Okay, so that actually means this polynomial equation is going to have 3 roots. It's going to have positive 3, negative I, and positive I as its root. So let's see how we can work backwards to find out what this polynomial equation is going to be. So let's come back to our notes here. So I've got positive 3, negative I, and positive I is also a root. Okay, so what we're actually going to do to find our polynomial equation is going to take each one of these roots and write them down as factors. So remember how, let me go back to our notes. So you can see here when we were talking about multiplicity, they said C would be our root if x minus c was our factor. So we're actually going to use that idea here. So if 3 is your root, then that means it comes from the factor of x minus 3, right? If negative I is our root, so negative I is actually going to come from the factor, which will be x minus negative I. So you'll actually end up having two negatives here. And then for I, we would say that's coming from the factor of x minus I. So what you have to actually remember is if the root itself is positive, then your factor will have a minus sign in it. If your, so for both of these, since these are positive values, we had x minus 3 and x minus I. Now this root here is a negative I, which means you will have two negatives, or basically go with the opposite sign, it will end up becoming a positive. So you will have x minus 3. These two negatives here become positive, so this will become x plus I, and then x minus I will be our other factor. And then of course, basically from this point on, you are going to multiply all of your factors to basically figure out what your polynomial equation is going to look like. So what I would actually do is I will start with these two, because you can see these are my conjugate pairs, right? I've got x plus I and x minus I, same terms. The only difference is the plus and the minus in the middle. So I would actually start by multiplying these guys. Now, if you remember, we have talked about difference of squares. So if I were to take a plus b and multiply it by a minus b, and if you FOIL that, you will end up getting a square minus ab plus ab minus b squared. Your middle terms is positive and negative ab, they cancel out, and they leave you behind with a square minus b squared. This is what we call as our difference of squares. So anytime you multiply conjugate pairs, a plus b and a minus b, you're going to get this answer of a square minus b squared. So when you multiply these conjugate pairs, you will end up getting x squared minus I square if you FOIL this, right? And then I'm going to keep that x minus 3 as it is in the front. So keeping that x minus 3 as it is, this guy here will become x squared minus, now again, I don't know if you remember this, hopefully you do. Remember I square ends up becoming negative 1, or you can think of square root of negative 1 as being I. So if you square on both sides, you're going to end up getting I square equals negative 1. So you're actually going to need to make that substitution. If you leave this at as I square, that's incorrect. So then I square will end up becoming negative 1, right? So again, your x minus 3 will stay as it is. The second one will become x squared. Negative and negative becomes positive. So this will end up becoming, I'm sorry, this should be equal to 0. So x squared minus negative 1 will end up becoming x squared plus 1. And then again, go ahead and FOIL these two parentheses. So we'll start with our first one, then the outer, then the inner, and then the last. So that will end up giving us x times x squared is x to the third power. X times positive 1 is positive x. Negative 3 times x squared is negative 3x squared. Negative 3 times positive 1 is negative 3. Now just clean this up. Put this in order from the highest degree to the smallest one. So you will have x cubed as our first term, then minus 3x squared plus x minus 3 equals 0. And this is what they were asking us to find. Find our polynomial equation where your roots were positive 3 and negative I, But because of the conjugate pairs theorem, we know if negative I is a root, that means positive I is also a root. And then you're just basically, if it's a positive root, you will have x minus that number. If it's a negative root, like you had negative I, then your factor ends up becoming x plus I, okay? All right, guys, so this is how we use the idea of the conjugate pairs theorem, and then working backwards, we can come up with what our polynomial equation is going to be. So, this would be something helpful, because if we knew that one of the conjugate pairs is a root for our polynomial function, then technically you've actually found two roots. But remember, we still need to narrow down our options, as we had seen in the rational zero theorem in the previous section, that we get a lot of options and we don't know which ones are going to work and which ones are not. So the other rule we want to introduce here is what we call as Descartes' rule of signs. So basically this is a method which helps us determine how many positive roots, how many negative roots, and how many imaginary roots is our polynomial equation going to have. So this helps us to determine the number of positive, negative, and imaginary solutions or roots, whatever you want to call it. So here they're saying for this rule, a solution of multiplicity k is counted as k solution. So if you have two factors which are giving you the answer 5, then we would say basically the 5 and the 5 makes up two of your solutions. So kind of what we have looked at with that multiplicity definition on the previous page. Okay, so they're saying when a polynomial function is written in descending order, which means start with the highest degree and keep going down, which is what this example here is showing us. They are saying a variation of sign occurs when the signs of the consecutive terms change. So what they're basically saying is start with the first term, make your way to the right till you get to the last term, and see how many times is the sign changing on your coefficients. So let's take a look at this guy here. This first term here is positive, right? Because this is positive 3x to the 5th power. But when I get to the second term, that's a negative, right? So my sign is changing right here because, or hold on a second, because I'm going from positive to a negative, right? So my sign is changing one time. But you will see now I'm going from negative 7x to the 4th to negative 8x to the 3rd. So I'm going from a negative to another negative term, which means my term, my sign did not change. Again, if I go from negative x cubed to negative x squared, again I'm going from a negative to a negative, which means again my sign did not change, so you cannot count that. But now if I go from negative x squared to the next term, that's a positive 3x, so I'm going from a negative term to a positive term, right? So that means there's a change happening. So that's my second change where my signs will change, right? Going from one term to the other. And then for the last one here, I'm going from a positive 3x to a negative 9, right? So again, you're going from a positive to a negative. So that's the third time that in this polynomial, your sign has changed. So that's what they mean when they say a variation of sign. And you can kind of read that here. They're saying the signs are changing from the first to the second term, which is what we had with this first arrow that I drew, from the 4th to the 5th term, so that's going from negative x squared to positive 3x, and from the 5th to the 6th term, which was going from 3x to minus 9. So they are saying there are 3 variations of sign for the original polynomial p of x. So this actually tells you the number of positive real solutions you can have. Okay, so the idea is if you have 3 times that the sign changed, or 3 variations, then that means at the most you have 3 positive solutions, right? Okay, and I'll get back to, there's a couple more details I want to talk about that. Now the other thing is, we are also saying that Descartes' rule requires that we look at p of negative x, which means you actually take your original polynomial function p of x and replace that x with a negative x. So again, instead of p of x, you're going to be looking at p of negative x. And then after you do that, you again count how many times have the signs changed. So what you'll notice from our original function, 3 of x to the fifth has now become 3 of negative x to the fifth. Negative 7x to the fourth is now negative 7 times negative x to the fourth, right? So everywhere that you had x in the original equation, you're now replacing all of those x's with the negative sign. So it becomes negative x. And then once you do your calculations, you will see we're going from a negative to a negative term, from the negative 3x to the fifth to negative 7x to the fourth. So no change. Then you're going from negative 7x to the fourth to positive 8x squared. So that's going from negative to positive. So that's one change. Then you're going from positive 8x cubed to negative x squared. So that's positive to negative. So that's a second change. Then we're going from negative to negative and negative to negative. So no change, right? So there are 2 times that when we look at p of negative x, your sign changes, which tells us that it's changing from the second to the third term, and it's changing from the third to the fourth term. So those are 2 variations. And this actually tells you how many negative real solutions are polynomial functions, right? So this is how you can calculate how many positive real solutions and how many negative real solutions you have. But like I said, there are a couple more details I wanted to talk about. So you've got your p of x equals 0 polynomial equation. It's got real coefficients written in the descending order. So they are saying the number of positive real roots is either equal to the number of variations, right? So like here, you saw there were 3 variations. So what this rule is saying, that you can have at the most 3 positive real roots, or you can lessen that by an even number. So which means you can actually start reducing them by 2. So that means if I have 3 variations and I reduce it by 2, that means you can have 3 positive real roots, or you can actually only have 1. And let me try rewriting that. Sorry about that, guys. This is just not cooperating how I would like to. Or you can have 3. Or remember, as I was saying, you reduce it by 2. So 3 minus 2 gives you 1. So you could only have 1 positive real root. Okay, and that's actually the same thing for the negative. So the number of negative real roots can be either equal to the number of your variations when we do p minus x, or again, it can be less than an even number. So you can see this p minus x gave us 2 variations. So this guy here had 2 variations, which means you can have 2 negative real roots, or if I reduce 2 minus 2, I can have 0 negative real roots. Okay, so the thing you have to think about here, this is a 5th degree polynomial. So if this is a 5th degree polynomial, it should have a total of 5 roots. So if it has a total of 5 roots, out of those 5 roots, if we are talking about 3 of them being positive here, that means I can have 3 positive real roots, and let's say it has 2 variations for the negative, right? Which means it can have 2 negative real roots. So that means these are two negative real roots, and 3 plus 2 adds up to 5, right? Which is the degree of our polynomial. So if 3 plus 2 adds up to 5, that means we have no room left for imaginary solution. So that means we can have 3 positive roots, real roots, 2 negative real roots, and 0 imaginary roots. But what if instead of having 3 positive, it has only 1 positive real root? So then we can say it can have 1 positive, right? If it has 1 positive, it can still have 2 negative roots. So if it has 2 negative roots and only 1 positive, then that adds up to just 3. And you should have a total of 5 roots, which means this actually opens up space for 2 imaginary roots. So you could have 1 positive, 2 negative, and 2 imaginary roots. Or, and I'm actually running out of space here. Or you could have basically, let's see, there's actually a couple more options here. You can have 3 positive, but instead of having 2 negative, you have 0 negative roots. So you could have 0 negative, which means again 3 plus 0 is 3. That's opens up space for 2 imaginary roots. Or we've got one more possibility where if you have only 1 positive real root, we have 0 negative real roots, which means 1 plus 0 is 1. That opens up space for 4 imaginary. So, and I know again this does not bring us down to a concrete way of knowing how many positives and negatives we have, but even if we can narrow down on the possibilities, because remember how last time when we were looking at the rational zero theorem, we were coming up with 16 options or 8 options. 8 was still not bad, but if you had 16 options or 20 options, that's a lot of options to go through. So, you know, this can kind of help you at least narrow down some of those options, and that's kind of where this idea of Descartes' rule comes into play. So let's actually look at a proper example so that I can actually show you how this rule works out to be. So remember, start by calculating how many times the sign has changed in your polynomial, both for the original polynomial or by using p of negative x, right, like we did in this example I just showed you. And then to count the number of positive real roots and negative real roots, it's either equal to the number of variations or you basically start subtracting by 2. So let's take a look at example 3 over here, and 4 I believe is also talking about the same thing. And then let's go ahead and see how we can use that to our advantage. Okay. All right. So let's come down to example 3 over here. We've got x to the third minus 5x squared plus 4x plus 3. So this original is your original polynomial that you're going to check your change of signs for. So you can see x to the third is positive. We are going from a positive to negative 5x squared, so that's positive to negative, so that's one change. Then you are going from negative 5x squared to positive 4x, so that's the second time our sign is changing. But now you are going from positive 4x to positive 3, so obviously your sign is not changing because you're going from positive to positive, so that is 2 variations. So 2 variations means we can have 2 positive real roots, or remember we start decreasing it by an even number, so 2 minus 2 would be 0, so you could potentially also have no positive real roots, right? So you can have 2 or you can have 0. All right. Then our next step was where you took this polynomial function and replace it with negative x. So all the original x's should now be replaced with negative x. So you would have negative x to the third power minus 5 negative x to the second power plus 4 times negative x plus 3. Okay? So if you remember, we had this discussion back in chapter 2. Also, if you have a negative base with an odd exponent, so negative x to the third power, that would end up giving you negative x cubed. Then if you have negative x to an even power, so like negative x to the second power, negative and negative will become positive, which means this negative 5 will actually stay negative 5, and negative x squared will end up now becoming positive x squared. And if it helps, write it out. So for that first one, you can take negative x multiplied into itself 3 times. So negative times negative is positive, positive times negative is negative, and you end up getting negative, oh, let me make that bigger, negative x to the third power, because you have 3 negative signs. For my second one, where you have negative x to the second power, that's just negative x times negative x, right? So the 2 negatives will become positive, and they will end up giving you a positive x squared. So that's why this term here ends up becoming just the negative 5 stays as it is, and then it becomes a positive x squared. So let me write that. Okay, and then here for the third term, you are multiplying positive 4 with negative x. So positive times negative will become negative 4x, and then that plus 3 of course will stay as it is since there's no x term with it. Okay, so now once you have this little calculation done, now go back and see how many times your sign is changing. So I'm going from negative x to the third power to negative 5x squared, so that's going from negative to negative, no change. Then you go from negative 5x squared to negative 4x, so again that's negative to negative, no change. So the only change that's happening is from going from negative 4x to positive 3. So I'm going from a negative term to a positive term. So that's one change. So I would say that's one variation. And one variation means I will have one negative real root. Now, I cannot do 1 minus 2, right? Because 1 minus 2 will give me negative 1. And you can have either no roots, or you can have 1, 2, 3, 4, 5, how many ever roots you can. But you can't really say my equation has a negative solution, right? You can say my equation has no solution. My equation has one solution, or like I said, my equation has 5 solutions, but you cannot really say my equation has a negative 1 solution. So you cannot, if you get 1 or 0, then that's really good, because that way I know I won't have to subtract by 2 in that case. So that means this equation here will definitely have one negative real root, but then it can have 2 positive or 0 positive. Now remember, this is originally a third degree polynomial. So since it has degree 3, that means it will have 3 roots total. So now that's the options we have to talk about. So what type of roots can it have? So basically, it can have 2 positive, 1 negative, and since this is a third degree polynomial and we can only have 3 roots, so that's 2 plus 1, which is 3, which means we have no room for imaginary solutions, right? However, we do have other options, because we said 2 roots which are positive, or 0 roots which are positive. So that means if I don't have 2 positive roots, I could have 0 positive, and remember these guys are real roots, real numbers. Only that last one is imaginary. And in the first option we had 0. So you can have 0 positive real roots, but you will still have that one negative real root. So no matter how many roots you check, one of them is definitely going to be negative. Now the thing is, if I add 0 plus 1, that only adds up to 1, and I should have a total of 3 roots. So that means if I only have one negative root, then that means it opens up space to have 2 imaginary roots. So these options have to always add up to whatever is the highest degree of your polynomial. So your two options would be you either have 2 positive real, 1 negative real, which means no imaginary, or you can have no positive real roots, you can have 1 negative real root, and that means we would have 2 imaginary. So it's going to be one or the other option, and of course if we solve this, then we will know what kind of roots we are going to have. Okay, and then we had another example here, and same thing, they're asking us to discuss the possibilities for the root. So we've got x to the 4th minus 6x squared plus 10 equals 0. So let's take a look at this example here. So remember, this is our original polynomial. So let's talk about its variations. You're going from positive x to the 4th to negative 6x squared. So that's one change. And then we are going from negative 6x squared to positive 10. So that's the second change. So that means we've got 2 variations here. 2 variations will mean 2. And then again, remember, we can subtract by an even number. So 2 minus 2 would be 0 again. So you can either have 2 or you will have none positive real roots. So kind of like what you saw in the previous example, right? And then let's see what happens when we replace our x with a negative x. So that would become negative x to the 4th power minus 6 times negative x to the 2nd power plus 10. So you can see how both these exponents are even numbers, right? 4 and 2. So negative x to the 4th power will end up actually becoming just positive x to the 4th power. Your negative x squared will also become positive, which means your negative 6 stays the same, right? So negative 6 stays the same. Negative x squared becomes positive x squared. So this guy just ends up becoming positive x, and then bring down that plus 10. Once you make this calculation, then you can see we are again going from a positive term to a negative term, and we're going from a negative term to a positive term. So 2 variations here again, and 2 variations here means that you can have either 2 or remember to decrease it by an even number again. So 2 minus 2 would be 0. So we will have either 2 negative real roots or we will have 0 negative real roots. So another thing to keep in mind, this is a 4th degree polynomial. So our degree is 4, which means we should have a total of 4 roots. So when we write our answer down, so we have either 2 or 0 positive and either 2 or 0 negative. So that means we can have 2 positives, and again these would be our real roots. We can have 2 negative real roots, and since 2 plus 2 adds up to 4 and we should have a total of 4 roots, that means you have no room left for the imaginary roots. So 2 positive, 2 negative, 0 imaginary, or you could still have 2 positive real roots, but instead of having 2 negative, what if we have 0 negative real roots? So if you only have 2 positive, 0 negative, that means we have just room for 2 imaginary roots, right? Or you could have 0 positive real roots, but you could still have 2 negative real roots. But again, that's not a total of 4, which means again, we could have 2 imaginary roots. So 2 negative, 2 imaginary. Or there's actually a fourth possibility where you could have 0 positive real roots. You could have 0 negative real roots. And that means if these guys are 0, that means all 4 of your roots are now going to be imaginary solutions. So the idea is, if you get 2 or 0 positive, 2 or 0 negative, you have to actually run through each and every scenario that you think is possible. So you can see we actually end up with 4 different possibilities here. So 2 positive, 2 negative, 0 imaginary, 2 positive, 0 negative, which means we just opened up space for 2 imaginary. If you have 0 positive, 2 negative, again, that means we opened up space for 2 imaginary solutions, or no negative roots, no positive roots in the real numbers, but all 4 of them happen to be imaginary. Okay? So those would be your 4 different options that is possible by using our Descartes' rule of signs. Okay? So that's going to be one rule which will help us narrow down our options. But the other thing that can also help us narrow down our options is what we call as the bounds on our roots, which means that if you can find an upper bound or a lower bound, so basically we would say your value of the roots cannot go beyond the upper bound, or the value of the roots cannot go anything less than the lower bound. So they're saying if a polynomial equation has no roots greater than c, and c is your upper bound, or on the other side, we can see if there are no roots less than c, then we can say c is the lower bound. Okay? So let's take a look at the theorem for this idea. So again, we're saying p of x is our polynomial. It has real coefficients, a positive leading coefficient, and they're saying synthetic division is performed by using x minus c as our factor, or basically you would be using that value of c to do your synthetic division. So they're saying if c, is a positive number, and all the terms in the bottom row. So when you're doing synthetic division, because remember that's what we're doing here, synthetic division. So if your c is positive and all the terms in the bottom row of your synthetic division are non-negative, then we would say c is the upper bound for your polynomial for the roots. Now if c, the number you're dividing by, that c happens to be a negative number, and the terms in the bottom row of your synthetic division will alternate in sign, then we would say c is a lower bound for our polynomial. Okay? Now one thing keep in mind, and I'll show you this when we do our examples, let's say in the bottom row for either one of these, if 0 ends up showing in the bottom row of your synthetic division, you can actually assign either a positive or a negative sign to that if it helps you with one of these calculations here. Okay, so just kind of keep in mind, even though normally we do not assign 0 a positive or a negative sign, for this purpose of this theorem on bounds, you can actually assign either a positive or a negative sign to 0 to see if it helps you in finding these bounds. Okay, so the example we're looking at here is our x cubed plus 3x squared minus 5x minus 15 equals 0, and they're basically asking us to use the theorem on bounds to see what those best integral bounds, or basically what your upper bound and lower bound for the root, lower bound for the roots is going to be. So let's take a look at this example here. Now this process can be a little tedious. So basically what we actually end up doing is, let's start with our calculation for the upper bound. So to find the upper bound, you actually start dividing by +1, +2, +3, +4, +5, and you keep going till you satisfy the condition. And remember, for the upper bound, you have to have all non-negatives if you're going to find the upper bound. So non-negative means you can have 0 or positive numbers. So we are looking for all non-negatives in our bottom row. Okay, so I am going to take our polynomial coefficients. So remember, x to the third has a coefficient of 1. I've got positive 3x squared, I've got -5, and I've got -15. And of course you can see there are no missing terms in here. So the first number I'm actually going to try is +1. So bring down the first number as it is, you don't change it. Then we do 1 times 1, which is 1. 3 plus 1 is 4. 4 times 1 is 4. Then add -5 with +4, which gives you -1. And technically, you can actually stop right here, because remember we said we are looking for non-negatives. So the moment you hit a negative sign, you know this guy is not working out for us. So now let's try same calculation again with a +2. So again, I'm using my polynomial here. 1, 3, -5, -15. Again, that first number comes down as it is. 2 times 1 is 2. I am adding 3 plus 2, which is 5. 5 times 2 is 10. +10, -5 will give me +5. So far we're doing really well. 5 times 2 is 10, but now -15 +10 will actually give you -5. So since we got that negative in the bottom row, this guy doesn't work out either. Okay, so basically you should not have any negative terms in there. 0 is okay, positive is okay. So the next number I'm going to try is now +3. And remember, we just keep going in sequence. So you start dividing by 1, 2, 3, 4, 5, and you keep going till you get all non-negatives in your bottom row. So again, our polynomial is 1, 3, -5, -15. So again, that first one comes down as it is. 1 times 3 is 3. 3 plus 3 is 6. 6 times 3 is 18. 18 minus 5, let's see, will be +13. And then 13 times 3 is 39, okay? And then from 39, we will be subtracting 15. So that's going to be 24. Alrighty, so you can see in our bottom row, we've got +1, +6, +13, and +24. They are all not negative, right? Non-negative, which means 3 is our upper bound. Alrighty, very nice. So we have found our upper bound, which means now we are ready to find the lower bound. And just to refresh your memory again, for the lower bound, we are looking for alternating signs. So this should be alternate signs in our bottom row. So you're still using obviously the same polynomial. So we've got 1, 3, -5, and -15. But now since we're finding the lower bound, we actually now start dividing by negative numbers, which means we're going to be dividing by -1. So again, start by bringing that positive 1 down. 1 times -1 is -1. 3 minus 1 is 2. And right here you will see my signs did not alternate, right? If I had my first number as positive, then for an alternate sign, my 2 should have been negative. And since my signs did not alternate, that tells me this guy is not our lower bound. So that means you can now move on to -2. So let's divide by -2. That's 1, 3, -5, -15. Okay, and again, my first one comes down as it is. 1 times -2 is -2. 3 minus 2 will again give me +1. So right here, same thing. I have +1, which means technically the second one should have been negative, but it's not a negative number, so my signs did not alternate. So this guy doesn't work out either, so it's not -2, which means we move on to -3 now. So 1, 3, -5, -15. Again, bring down that one, the first one down as it is. 1 times -3 is -3. 3 minus 3 is 0. So this is kind of what we were talking about. When you got 0 in the bottom, and this was this little sentence right here, if you got 0 in the bottom row, you can assign it either a positive or a negative sign if you wanted the signs to alternate. So you can actually think of this 0 as being a -0, because my 1 is positive, so you can think of this 0 as being negative. Obviously, when you multiply 0 times -3, you get 0. And that will end up giving us -5 and 0, which will again end up giving us -5, right? So if 1 is positive, we are thinking of 0 as being negative, which means technically this third term should have been positive. So again, you can see my signs are actually not alternating, because I'm going from negative to negative. So that actually tells me this guy is also not our lower bound. And since he's not our lower bound, move on to -4. So dividing by -4, bring the 1 down. 1 times -4 is -4. -4 plus 3 gives us -1, so that's good. Our sign is alternating right now. Then -1 times -4. Negative and negative becomes positive, so this guy ends up becoming +4. Then when you do -5 plus 4, it actually gives you a -1 again. So you can see my signs did not alternate, because if the second term was negative, this guy should have been positive. So again, since my signs are not alternating, -4 is not our lower bound either. So -4 does not work, which means now you move on to -5. So 1, 3, -5, -15. Bring down that 1 as it is. 1 times -5 is -5. 3 minus 5 is -2. So again, my signs alternate, so this is good. Negative times negative will be positive, and then 5 times 2 is 10. So that's +10 minus 5, which will give us +5. So my sign is alternating so far. We're good. 5 times -5 is negative 25, and then negative 15 minus 25 will actually give us negative 40. So here you can see my signs are alternating, right? I've got positive 1, negative 2, positive 5, negative 40. So we're going positive, negative, positive, negative. Since our signs are alternating, he is going to be our lower bound. So what this actually tells us that whatever solution you find for this polynomial, which means you're basically trying to find the value for x, right? So whatever solutions you find, hold on a second. They have to stay between these numbers, which means your bounds are going to be that the x value has to be between negative 5 and positive 3. So anything outside of that, if you get as your options in the rational zero theorem, you can actually discard them. So we will say x is going to be between 3, which was our upper bound, and negative 5, which is our lower bound. So basically your x value has to stay between those two numbers. Okay? So that's kind of the idea behind using this theorem on bounds. Now this can obviously, as you see, can get pretty tedious, because for the upper bound we start dividing by positive 1, positive 2, positive 3, and you keep going till you find all non-negatives in your bottom row. For the lower bound, we're looking for alternating signs, which means again you start dividing by negative 1, negative 2, negative 3, negative 4, negative 5, as far as you need to go till you found those alternating signs in your bottom row, right? So that's kind of how this theorem on bounds works. So this was example 5. And then the last example I actually want to talk about in this section is seeing how we can use all of this information to our advantage. And they're saying find all the solutions for 2x to the third minus 5x squared minus 8x plus 5 equals 0. So let's take a look at this last guy here. So we're actually going to start with our rational zero theorem first. So remember, this is where we take the positive factors of our constant term, which is the number 5. So 5, of course, is only going to be 1 and 5, right? So not too bad. Then you are going to take the positive factors of the leading coefficient, which is 2, from the 2x to the third. And again, 2 is only going to be 1 and 2. So remember, we call this variable p, we call this q. So you're going to take p divided by q, and that will give you 1 and 5, which is our p, divided by 1 and 1, and then 1 and 5 divided by 2 and 2, right? Because each of the p values has to be divided by each of the q values, and then putting it all together, your rational zeros are going to be, and these are all the possible rational zeros, because we don't know which one of these are going to work, right? So that's going to be positive or negative 1 from this guy, positive or negative 5 from this guy, or positive and negative 1/2, or positive and negative 5/2. So you're looking at about 8 possibilities here, right? So that's your rational zero theorem. Now, let's talk about Descartes' rule of signs. I don't know if you recognize this name of Descartes or not, but this is the same mathematician who gave us the Cartesian coordinate system, or our rectangular x and y plane that we use for graphing. So it's actually the same mathematician who came up with this. So remember, for Descartes' rule, you look at the original polynomial function, which in this case is 2x cubed minus 5x squared minus 8x plus 5, right? So we can see you're going from a positive to a negative. That's negative to a negative, and then we're going from a negative to a positive again, right? So that's two variations. So that can mean either 2, or remember we subtract by 2. So either 2 or 2 minus 2 is 0. So we can have 2 positive real solutions, or we can have 0 positive real solutions, right? Then the next one we do is where we replace our x with negative x. So that ends up giving us 2 negative x to the third minus 5 negative x squared minus 8 negative x plus 5. And this will end up becoming, remember, my negative x to the third power will keep a negative sign. So this term will actually end up becoming negative 2x to the third, because we get a negative left over from our x. For the negative 5 parentheses negative x squared, the negative x squared will become positive, because negative times negative is positive, which means the 5 will keep its negative sign. So this will be negative 5, and this guy becomes positive x squared. For your third term, you have negative x multiplied with negative 8, right? So negative 8 times negative x, the two negatives become positive, and this ends up becoming positive 8x. And then the plus 5, will stay the same, right? Since there was no x term in there, so the 5 will stay as it is. Now, let's look at how many variations we've got. So I'm going from negative 2x cubed to negative 5x squared, so that's negative to negative, no change. But if I go from negative 5x squared to positive 8x, that means I'm going from negative to positive, so that's one change. But then when I go from positive 8x to positive 5, that's no change, because you're going from positive to positive. So that means we will actually only have one variation here. And that's a good sign, because if you have only one variation, that means you will definitely have exactly one negative real root. And then we can potentially have 2 positive or 0 positive real roots. So let's see what kind of roots this ends up having. So I will call these as possible roots again. So that means you can have 2 positive, 1 negative, and this is a third degree polynomial, so 2 plus 1 is 3, which means that would be 0 imaginary. Or if you don't have 2 positive, which means we could have 0 positive roots, but that means we're still going to have 1 negative, right? Because we only had one variation. So the 1 negative is definitely going to be there. But that only adds up to 0 plus 1, which is 1, which means there's a possibility we could have 2 imaginary roots, okay? So basically we are saying out of these options that we have here, which is 4 positives and 4 negatives, we could have 2 positive, 1 negative, or from all of those options, maybe I only have 1 negative real root and the other 2 end up becoming 2 imaginary roots. So I can have 2 positive, 1 negative, or 1 negative and 2 imaginary roots for this polynomial. So that's how that Descartes' rule of signs comes into play. And now, the third thing we had talked about was that theorem on bounds. So let's see what the bounds are for these roots. So for theorem on bounds, let's start by talking about the upper bound. Remember guys, for the upper bound, you are looking for non-negatives, right? So we would start dividing by positive 1. Now again, your polynomial is 2x to the third power. That's minus 5x squared minus 8x, and positive 5, right? Again, we are not missing any terms, so we don't have to worry about putting zeros anywhere. Now take that 2 down. Then 2 times 1 is 2, minus 5 plus 2 is minus 3, right? And I've already hit my negative, so that means 1 is not our upper bound, because remember, these guys should be non-negatives. So let's divide by 2 now. So let's see, we'll have 2 minus 5 minus 8 positive 5. So that's going to be 2. 2 times 2 is 4. Negative 5 plus 4 is negative 1. Again, we've hit a negative number, which means this guy doesn't work. Let's try with 3. So that's 2 minus 5 minus 8 positive 5. Bring down the 2. 2 times 3 is 6. 6 minus 5 is positive 1. That's good. 3 times 1 is 3, which will actually end up giving me negative 5. And I've hit a negative number on my bottom row, so the key doesn't work. Okay, that does not look good. Let's see what the next one gives us. So let's divide by 4. 2 minus 5 minus 8 positive 5. So again, bring down the 2. 4 2s are 8. 8 minus 5 will be what? 3. 4 times 3 is 12. 12 minus 8 is 4. 4 times 4 is 16. And of course, 16 plus 5 will be 21. So as you can see, these are all positive numbers on my bottom row. So that makes this number our upper bound. Okay. So what this actually tells me, since positive 4 is your upper bound, that means you can see how this guy here has positive 5. You won't need to use positive 5 as one of your solutions, because positive 1 is less than 4, positive 1/2, positive 5/2. 5/2 is basically 2.5, which means you can discard positive 5 from your roots, because he does not satisfy this upper bound of positive 4, right? Anything greater than positive 4 is not included. Now, let's find the lower bound. So for, remember, lower bound, we are looking for alternating signs in our bottom row. Okay, so let's start by, again, this time we're dividing everything by negative 1. Can't write, can I? Okay, so again we have 2 minus 5 minus 8 positive 5. Bring down the 2. 2 times negative 1 is negative 2. Negative 5, negative 2 is negative 7. So we're alternating so far. Negative 7 multiplied with negative 1 will be positive 7. Negative 8, positive 7 gives us negative 1. So no alternating sign here, which means negative 1 actually is not our lower bound. Now let's try it with negative 2. We have 2 minus 5 minus 8 positive 5. Bring down the 2. 2 times negative 2 is negative 4. Negative 5, negative 4 is negative 9. And then negative 9 multiplied with negative 2 will be positive 18. 18 minus 8 is positive 10. So we're alternating in signs so far, so that's good. And then when I multiply 10 times negative 2, it gives me negative 20. Negative 20, positive 5 will give us negative 15. So you've actually got positive 2, negative 9, positive 10, negative 5, right? So positive, negative, we are alternating. So that was good. We didn't have to go too far. And negative 2 is our lower bound. So that means our x is going to stay between 4 and negative 2. So that also means anything below negative 2 is gone. So you can actually discard negative 5. Negative 1 we can keep. Negative and positive 5 are both gone. Actually, we can keep both positive and negative 1. Because remember, your numbers have to be between negative 2 and 4. And actually, they can be including negative 2 and positive 4. So it can be including those. So anything between negative 2 and positive 4 is okay. So that means positive 1, negative 1 are fine. Both positive and negative 5 are not. So we discard them. Both positive and negative 1/2 are safe. Positive 5 over 2, which is again, as I told you, 2.5. Positive 2.5 is okay, but negative is not, which means I am also discarding negative 5/2 because negative 2.5 or negative 5/2 is going to be outside of this theorem of bounds that we just calculated. Okay? So that means, let me go back here. That means these guys are gone. And the negative 5/2 is gone. So remember when we did Descartes' rule of signs, we said we should definitely have one negative real root as part of our solution. So at this point, what you can do is start checking these negative options. So remember, the only negative numbers at this point you have to check. And let me see if I can circle them. So we only have negative 1 left over and negative 1/2 left over, right? Because negative 5 got cancelled out. Negative 5/2 got cancelled out. So if you check any of these two roots, you should be able to see which one of them will actually be part of the root for our original polynomial. So what I will actually do is for this negative 1, you can actually come back to where we were doing this lower bound calculation, because I've already done most of it, right? I am dividing by negative 1. So go all the way and see, do you get a 0 remainder in your synthetic division? So all we have to do at this point, and I'm going to do this in orange so you know that we're checking for this. So negative 1 multiplied by negative 1 will give us positive 1. And then when I add 5 plus 1, I get 6, right? I am not getting a 0 remainder, which tells me negative 1 is not a root for our polynomial. So that tells me that this negative 1 does not work out either. Or you know what? Let's do that in orange. So negative 1 is not a root, which means the only thing we got to check for now is that negative 1/2. So now, after we have narrowed those 8 options down, let's check if x equals -1/2 is a root or not. Okay, so we'll take that -1/2. And we're checking it with our polynomial 2 minus 5 minus 8 positive 5. So bring down the 2. When I multiply, and let's do that as scratch work here, when I multiply 2 with negative 1/2, my 2 and 2 will cancel out, basically giving me negative 1. So then this guy becomes negative 1. Negative 5, negative 1 is negative 6. Then we are multiplying, let's do it this way. We're multiplying negative 6 with negative 1/2. So 2 goes into 6 3 times. So that's negative 3 times negative 1, which will be positive 3. So then this guy becomes a positive 3. Negative 8 plus 3 is negative 5. And then when I multiply negative 5 with negative 1/2, since 2 does not go into 5, you actually end up getting positive 5/2 as this guy here. So now I am adding 5 with 5/2. So find your common denominator, and of course, since you're adding, you know you're not getting a 0 denominator, because you'll end up getting 10 plus 5 over 2, which is 15 over 2. So not a 0 remainder, right? So interestingly enough, negative 1/2 is also not a solution for our polynomial. So we still have positive 1, positive 5/2, positive halves and positive 5/2 left to check. You can again actually check for positive 1 right here where we were doing our upper bound calculation. So just go ahead and complete this calculation here. You've got negative 3 times 1, which is negative 3. Negative 8 plus negative 3, so that's 8, 9, 10, 11, right? Negative 11. Then we do negative 11 multiplied by positive 1, which is negative 11. And of course, you can see this is not a 0 remainder either, because you got negative 6. So this is not a root either. So actually, both positive and negative 1 did not work out in this case. So now let's actually check and see if positive 1/2 gives us anything or not. So is x equals 1/2 a root? So 1/2, and our polynomial is 2 minus 5 minus 8 positive 5. So let's start by bringing that 2 down. Then we are multiplying 2 times 1/2. So the 2's cancel out, giving us 1. So that's a positive 1. Negative 5, positive 1 is negative 4. So let's multiply negative 4 with 1/2. So 2 goes in itself once, goes into 4 twice. So that's negative 2, positive 1, which is negative 2. So we've got negative 2 here, negative 8, and negative 2 gives us negative 10. We are multiplying negative 10 with 1/2. So 2 again goes into itself once, goes into 10 5 times, and we end up getting negative 5. And look at that, positive and negative 5 will end up giving us a 0 remainder. So if you have 0 remainder, then we can say yes. Oops. Let's do it this way. this is a root, right? So we've got our one of the roots, and this was actually a positive number, right? So since this is a positive number, going back here, you're actually looking at this option here, because if you got a positive number, that means we should have one more positive root and we should have one more negative root. But you know what? Those answers are actually coming from this part here, from our quotient, because this was your remainder. So now what you're going to do is take that quotient and solve that to find those other roots that you have. So this guy works out. That's good to know. And now let's use our quotient. Which will be 2x squared. Remember, this is a third degree polynomial, so your quotient will be 1 degree less than that. So that's 2x squared minus 4x minus 10 equals 0. Even right here in your synthetic division, here you should see that all of these terms have a 2 in common, so you can actually reduce this quotient by 2. So if you basically take each term and divide it by 2, you should actually end up getting x squared minus 2x minus 5 equal 0. If you don't recognize that there's a 2 common in all these terms, then just keep 2x squared minus 4x minus 10 and use that. And in this case, actually factoring does not work, so you will have to use quadratic formula. So you can keep those original, or if you recognize that everything has a 2 in common, you can reduce your quotient down. So you can use this. So it's up to you. Now let's use our quadratic equation to find out what those other 2 roots are going to be. So that's going to be negative b, and in this case b happens to be negative 2, plus or minus square roots. Again, that's b squared, which is negative 2 squared. 4 times a is 1, c is negative 5, divided by 2a, which is again a is 1. So this will give us positive 2 plus or minus, that's negative 2 squared, which is 4. Negative 4 times 1 times negative 5 will be negative and negative positive, so that's positive 20. And then 2 times 1 is 2. So you end up getting 2 plus or minus square root of 24 over 2, right? And then your square root of 24, you can write 24 as 4 times 6. Square root of 4 is 2. 6 will continue to stay inside. So I'm actually going to write this as 2 plus or minus 2 square root of 6 over 2. And since you can see I have a 2 here, a 2 with my square root, and a 2 on the denominator, I'm going to write this guy as 2 divided by 2 plus or minus 2 square root of 6 divided by 2. So I'm just splitting that denominator between our two numerators. 2 goes into itself once. These 2's cancel out, leaving you with square root of 6. So you're actually getting 1 plus or minus square root of 6 as our 2 other roots. So we've got positive 1/2 from here. So our final roots, or you can think of these as your solutions, are going to be positive 1/2. So I'm actually going to go all the way to the top. So that positive 1/2 is actually coming from this list that we got from our rational zero theorems. Then Descartes' rule told us we should have 2 positives and 1 negative, 0 imaginary. So let me show you that. So 1/2 is one of our positives, and then 1 plus square root of 6 is actually our other positive root, and then 1 minus square root of 6 is going to be your negative. So this is our positive real. This is our positive real. And this is our negative real root. Okay? So that's what Descartes' rule told us. 2 positives, 1 negative, 0 imaginary. And then theorem on bounds told us our number should be between positive 4 or between negative 2 and positive 4. So these numbers are definitely going to be between negative 2 and positive 4. If you just use your calculator, 1 plus square root of 6 is approximately 3.45. So this guy is approximately 3.45. So of course you can see that is between negative 2 and positive 4. Let me write that a little bit better. And then for the 1 minus square root of 6, that is approximately negative 1.45. And of course 1/2 is approximately, or not approximately, exactly 0.5. So you can see all of these numbers are between negative 2 and positive 4. So you can see how these different rules and theorems kind of help us narrow down our options, but none of them are going to tell us what our exact root is going to be. So remember, when you write your solution set, don't write those decimal approximations. Write the exact answer. So you will write 1/2, 1 plus square root of 6, and 1 minus square root of 6 as your solutions. Okay, so this is going to be your solution set. So I know this one took us a little bit, sorry guys, whoa, so I don't know what I'm doing. So this one took us a little bit of a calculation. Now, you know, of course, there are going to be some examples which may not take us quite as long. Some of them may take us a little bit longer, but this is kind of the idea of how you bring all of these rules together. The only other option you would have is, once you found your rational zeros, checking to see out of those 8 options which ones work. So that would be another thing you could try, but you know, of course, that's going to be equally tedious that you have to try all of those. So you can kind of see what the process for this example was. Okay, so this is going to be your example 6, which was the last one. So that's kind of how this rules, like I said, and theorems work out. So again, if you have any questions about section 3.3, let me know, and we can go over those questions in class. All right, guys, have a wonderful day. Be careful, and I will see you guys in class. Take care. Bye-bye.